Arc length, section 12.5, arc length and curvature. So we begin with arc length. Okay. For a curve, a smooth curve, given by r of t equal to x of t in the I direction plus y of t in the j direction plus z of t in the k direction. The arc length on the interval from a to b is given by s equal to the integral from a to b of the magnitude of r prime of t squared dt. Not squared. Silly, not squared. There we go. Okay, so that is equal to the square root. I'll just go to the next line. The integral from a to b of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. All right, so let's put a box around that because that is our formula for arc length. All right, so let's do an example with this. So this is going to be our example here. Find the arc length on the interval from 0 to 2 for r of t equal to, we have t in the I direction plus 4/3 t to the 3/2 in the j direction plus 1/2 t squared in the k direction. All right, the derivatives of each of these, we have x of t is t, y of t is 4/3 t to the 3/2, and z of t is 1/2 t squared. So each derivative here is given by these. So it's going to be 2t to the 1/2, and z prime of t is going to be just equal to t. Okay, so then the arc length is the integral from 0 to 2 of the square root of 1 squared plus 2t to the 1/2 squared plus t squared dt. So that's the integral from 0 to 2 of 1 plus 4t. Yeah, just because t to the 1/2 squared is just t plus t squared dt. I'm going to rewrite these in descending power order just so that we can complete that square. Plus 1 dt. Okay, and we do need to go ahead and complete the square here. So complete the square, and remember we do that if given ax squared plus bx plus c, we're going to add and subtract, so we don't change any values, we're going to add it and subtract it, b over 2a squared. Okay, so that's what we're going to add and subtract. All right, so my b in this scenario is 4, so half of that squared is 4, so we're going to add and subtract 4. So this is going to be equal to the integral from 0 to 2 of the square root of t squared plus 4t plus 4 minus 4 plus 1 dt. Okay, so the reason we do this is because this is now factorable as a perfect square, so the integral from 0 to 2 of t plus 2 quantity squared, minus 4 plus 1 is minus 3 dt. Okay, and this we can complete with a lovely trig substitution. However, depending on the instructions that we're given, we can use the calculators to evaluate this, right? We can get a decimal approximation. So let's use our calculators. Use the calculator and give an approximation rounded to 3 decimal places. So rounded to the nearest thousandth. Okay. All right, and that comes out to be approximately 4.816. All right, now for those of you that are curious, if you do not remember how to do the trig substitution, we could have done this. Okay, so by hand, what we would do is we would let, this has the form u squared minus a squared, so we would let u be equal to a times secant of theta, then du would have been equal to a times secant theta tangent theta d theta, we could have made our substitutions and simplified, and then followed through to find our integral there. Okay, but since this is a definite integral and we just needed an approximation, doing it in our calculator worked out great. Okay, so let's do another example. So this one is involving a helix. So a helix is a spiral, like a DNA is a double helix because it's two spirals going around each other, right? So it's just a spiral or a spring. We've seen these before, just kind of look like this. Right, so it's kind of, this one's going up in this way. Okay, so you can kind of see that there. So that's what it looks like. So let's find the arc length of a helix. So our function here is going to be given by b cosine of t in the I direction plus b sine of t in the j direction plus the square root of 1 minus b squared times t in the k direction. Well, of course I did. Times t in the k direction. Okay, so let me put these back. There we go. Okay, so this is going to be our formula for the helix, and we're going to do this for t between 0 and 2 pi. All right. Okay, so then our integral, our arc length is equal to the integral from 0 to 2 pi of the square root of, and we need the derivatives of each of these component functions. So for the first one, that's going to be b times negative sine of t squared plus b times cosine of t squared plus the square root of 1 minus b squared squared dt. All right, so let's see what we get. So this is the integral from 0 to 2 pi of the square root of, all right, so b squared sine squared of t plus b squared cosine squared of t plus 1 minus b squared dt. All right, b squared sine squared t plus b squared cosine squared t. Sine squared plus cosine squared is 1. Factor out the b squared, and here's what we have. 0 to 2 pi times the square root of b squared plus 1 minus b squared dt. Well, of course, that cancels, and all we have left is the integral from 0 to 2 pi of 1 dt, the square root of 1, which is 1. Integrating that, what we get is 2 pi. Pretty straightforward on that one. Okay, so arc length can also be given as a function of t. So let's take a look at that. Arc length, let's just say the arc length function. Okay, so for a smooth curve given by r of t equal to x of t I direction plus y of t in the j direction plus z of t in the k direction. All right. Let's see, on some closed interval a to b. Okay. Then the arc length function is given by s of t, so it's not just s anymore, it's a function now, so s of t equal to the integral from a to t of the magnitude of r prime of u du. Let's fix that. It's supposed to be du. So that's equal to the integral from a to t of the square root of x prime of u squared plus y prime of u squared plus z prime of u squared du. All right, so you may be wondering, why isn't this integral growing from a to b? Well, because this is a function of t. It depends on what it is. T is in this interval from a to b. Okay, so we're beginning at a and moving up to whatever t is. And this arc length s is called the arc length parameter. All right, and there's a good question in WebAssign that'll help walk you through this arc length parameter and how we get that and how we use it. Okay, so what this formula is doing is this is giving us, so S of t is measuring the distance along a curve from the point x of a, y of a, z of a, so that's our initial point, to the point x of t, y of t, z of t, right? Okay, and furthermore, if we employ the second fundamental theorem of calculus here, we will find that ds dt is equal to the magnitude of r prime of t, or we could write that as ds is equal to the magnitude of r prime of t dt, right? Okay, so let's go ahead and do an example here. So example, let's find the arc length function. For r of t equal to 3 minus 3t in the I direction plus 4t in the j direction on the interval from 0 to 1. And then write r as a function of the parameter s. Okay, so we're going to need to find the magnitude of r prime. So r prime of t is equal to negative 3, 4. So the magnitude of that is the square root of 9 plus 16, which is equal to 5. Okay, so then our arc length, s of t, is equal to the integral from 0 to t of that magnitude. So that's going to be 5 integrated with respect to u. So that's equal to 5 u evaluated from 0 to t, which is just 5t. Okay, so s of t is equal to 5t. So there's the first part of our answer. That's our Arclength function. Okay, so now we're going to use that to rewrite r as a function of s. Okay, so we have s is equal to 5t, which means t is equal to s over 5. So r of t was equal to 3 minus 3t in the I direction plus 4t in the j direction. Okay, so then r of s is going to be equal to 3 minus 3s over 5 in the I direction plus 4 times s over 5 in the j direction. Okay, and we have to tell them what s is running between. So t was between 0 and 1, so s is between, so t was between 0 and 1. So s is going to be between 5, 0, and 5, because s is 5 times t. 5 times 0 is 0, 5 times 1 is 5. Okay, so this is for 0 between s and 5. Okay. All right, so something interesting about the arc length parameter. The magnitude of r of s, oh no, not prime, there we go. Need an arrow up there. There we go. So the magnitude of r prime of s is equal to 1. And that's for any parameterized curve that it's parameterized by its arc length. Okay, so this is a big deal. So the arc length parameter implies that this is the case. And furthermore, if any t has the magnitude of r of t equal to 1, then t is representing is the arc length parameter. And t is the arc length parameter. Oops, arc length parameter. There we go. So that actually makes some calculations very nice. If we can parameterize something by its arc length, then its magnitude is just 1. And so that's going to make a lot of future calculations very, very nice. All right, so now let's talk about curvature. So curvature, which is denoted K for curvature, okay, that is a measure of how quickly a curve is curving. So let's see here. The flatter a curve is, so the less curvy, the flatter a curve, the smaller the curvature. Curvature. So what I mean by that is if I've got a curve that curves like this and a curve that just is very gentle, right? This has a much higher curvature and this has a lower curvature because it is not curving nearly as quickly. Okay. All right. So suppose R of S, is the equation of our curve is the vector valued function that gives us our curve, where S is the arc length parameter. There we go. Then the curvature, K, is equal to the magnitude of dt over ds, which is equal to the magnitude of t prime of S. So this is the curvature at S. Okay, the curvature at S. So that's our curvature. And one really kind of cool thing that happens that we see here is that if we were to calculate the curvature of a circle, and this is shown in your book, but if you wanted to calculate the curvature of a circle, the curvature of a circle is inverse of its radius. So if you have a circle of radius 1 over 3, God help me. If you have a circle of radius 3, the curvature is 1 over 3. Okay, and what that means is that the larger the circle is, the greater the radius is, the smaller the curvature is, and that makes sense. A very small circle has a very quick curve, whereas a very large circle would have a much slower curve. Okay, now that's the formula if our position vector valued function is parameterized in S. But if it's not parameterized in S, then we have another formula. So here, so for R of t, so for a curve given by R of t not parameterized in S, then the curvature K at t, then the curvature at t, I need to make sure I'm clear about that. That curvature is equal to the magnitude of t prime of t divided by the magnitude of r prime of t. Okay, so that's equal to the magnitude of r prime of t crossed with r double prime of t divided by the magnitude of r prime of t cubed. Okay, so the magnitude of t prime of t is equal to the magnitude of r prime of t crossed with r double prime of t divided by the magnitude of r prime of t squared. So we put all that together to get this lovely formula. Okay, so it's much more complicated formula than if it's parameterized by S, but we can do it this way. We can definitely do it this way. So let's go ahead and work an example. Let's find the curvature of r of t equal to 2t in the I direction plus t squared in the j direction minus 1/3 t cubed in the k direction at any t. Okay, so to do this, we are going to need r prime of t and r double prime of t. So r prime of t, that is equal to, I'm just going to do this in component notation here. So that's equal to 2t and negative t squared. R double prime of t is 0 to negative 2t. So we are now going to need to cross these and find that magnitude. So r prime of t crossed with r double prime of t. Not the magnitude, not yet. We'll get to the magnitude in a second. That's going to be the determinant, I, j, k, and we have got 2 2t, negative t squared, 0 to negative 2t. Okay, so that's going to be 2, back that train up, all right, negative 4t squared minus negative 2t squared, okay, in the I direction, minus, because it's the j, minus negative 4t minus 0 in the j direction, plus 4 minus 0 in the k direction. So this comes out to be negative 4t squared plus 2t squared. Really? I think we can do better than that. Let's see. So negative 4t squared plus 2t squared is negative 2t squared in the I direction, positive 4t in the j direction, and positive 4 in the k direction. So the magnitude of this, the magnitude of r prime of t crossed with r double prime of t, is equal to the square root of 4t to the 4th plus 16t squared plus 16. All right, see if we can simplify that. So we can definitely take out a 4. We get t to the 4th plus 4t squared plus 4. So that's 4t squared plus 2 quantity squared. So that's 2 times t squared plus 2. All right, and then we need to find the magnitude of just r prime. So let's go back up and here, I'm going to put a circle around this so I don't lose it. Okay, so now let's go back up and find r prime. So r prime of t, so the magnitude of r prime of t is equal to the square root of 4 plus 4t squared plus t to the 4th. So that's the square root of 2 plus t squared, squared. So that's equal to 2 plus t squared. Okay, so I'll put a little circle around that so I don't lose that. Then our curvature, k, is equal to 2 times t squared plus 2 divided by 2 plus t squared. All right. 2 plus t squared cubed, because it's the denominator, right? So then we get one of these to cancel with one of those, and what we are left with is that k is equal to 2 divided by 2 plus t squared squared. Okay. So now let's go on. We're going to talk about acceleration, speed, and curvature. So acceleration, speed, and curvature. All right. So given r of t is our position vector for a smooth curve, the acceleration vector is given by a of t is equal to the second derivative of s with respect to t of the tangent vector plus k times ds dt squared of the normal vector, where k is curvature and ds dt is the speed. Okay, so let's take a look at the tangential and normal components of acceleration in this situation here. So let's just do this through an example. Okay, so find a sub t, not a sub t vector, there we go, a sub t and a sub n for the curve given by r of t is equal to 2t in the I direction plus t squared in the j direction minus 1/3 t cubed in the k direction. Okay. Well, that's convenient because we already know the curvature. We just saw that a second ago. So we know that the curvature for this is given by 2 over 2 plus t squared quantity squared. And we also saw that the magnitude, well, let me back this train up a sec here. We also saw the ds dt, which is the speed, which is just the magnitude of the velocity vector, which is r prime. We also saw that that was t squared plus 2, so we've already got that one in place. Okay, and we can use these to find our acceleration components in the tangent direction and in the normal direction. Okay, so let me go back up here. So it's not a good idea to lecture at this hour. So I do apologize for all my tongue-tiedness. But we've got our acceleration. The component in the tangent direction is the second derivative of s with respect to t, and the component in the normal direction is k, the curvature, times the speed squared. All right. So we come back down here, and we need to find a sub t, and we want to find a sub n. Okay, so a sub t is the second derivative of second derivative of s with respect to t. So we already know the first derivative. The first derivative is t squared plus 2, right? That's ds dt. So we're going to take ds dt of t squared plus 2. So that's going to be equal to 2t. Derivative of 2 is 0. So that's equal to 2t. So there you go. There's our tangent component. Now, the tangent component of the acceleration. So now let's find the normal component of the acceleration. So that's going to be equal to k times the speed, ds dt. Well, we already found ds dt, and curvature. So that's going to be equal to 2 times t squared plus 2 over 2. I'll write it the same way I have it up there. 2 plus t squared squared. So we cancel out one of those and we get 2 over 2 plus t squared. Except that's not what it said. Okay, go back up to the formula. Go back up to the formula. There we go. I missed the square. Got to watch out for this. So I missed the square. So come back down here and we got to square this, right? So I have to square this. So what I wrote right here was incorrect. Right? Because this 2, this should be squared. So then it's going to cancel completely, leaving me with just a 2, for goodness sake. So our acceleration vector here is given by, all right, 2t in the t direction plus 2 in the n direction. Goodness sakes. Okay, so there's that. The individual components are here, and then there's the actual acceleration vector. Okay, so I think I've butchered this enough for one night. Let me leave you with one last thought here. It's having to do with frictional force. So frictional force. So just one last thought. The frictional force must be equal to, let me just write this down. The frictional force must be equal to the mass times the normal component of acceleration. Okay? So if you're asked to find the frictional force needed to keep something from flying off of a curve or a bend or whatever, that's the idea behind it. The frictional force must be equal to the mass times the normal component of acceleration. All right, guys, I've got to cut it off here. If you've got any questions about this unit, and I would not be surprised if you do, please do let me know, and I'll be happy to go over it with you. All right? Thanks.